present and future values. So remember that if we're going to look for the present or future value of a single payment that is compounded continuously, we have two equations that we use to model this scenario. Future value can be found by doing PE to the RT. Remember, P is your initial one-time deposit, R is your interest rate, and time T is in years that you leave your investment in. We can solve this equation for P to get a formula for the present value. When we do that, we get that present value equals future value e to the negative RT, where again, R is our interest rate and time T is in years. So if we wanted to know how much money we would need to invest today to have a certain amount of money in the future, then using the present value equation would be the right one. In both of these scenarios, we're making a one-time lump sum investment and seeing how that money changes over time. However, sometimes we want to look at what happens if we're making regular payments into an account. This is especially true for companies and places that make lots of investments. So if we're making continuous payments, how does this impact our formula, and how can we adjust this to find the things that we're interested in, which are present and future value? So when companies are investing the revenues that they're making investments at every single moment in time. So instead of one payment, they're doing this in what's called a continuous income stream of investing. This stream can vary from time to time with more money coming in than other times. So what we need to do in order to figure out how this money will work as future and present value is to count it as a yearly investment. And we do this by using the notation S of T dollars per year. So if we take all these deposits over the 1 year term and we sum them up to figure out the rate at which we are investing, now we're continuously depositing our income stream for our investment. Now, because this is the rate at which we are investing, and we are doing this from year to year, to find the total change in dollars that we have, we would need to look at the area under the curve of this S of T function. So even though it's a constant rate, so maybe $5,000 a year, $20,000 a year, it's still a rate. So what we're going to do is we're going to use the integral to figure out the things we want to investigate regarding this money. So the present value will be the integral from 0 to m of S of T e to the negative RT dt. So notice here that t has become our variable in our integral, which means that we need a new variable to represent how many years we're leaving our investment in. So m is now going to represent the number of years. S of t is the rate at which we are putting in the money, and e to the negative RT tells us things like the interest rate and how to bring all these future payments back into the present. So to calculate the present value, we need to look at the area under the curve for all potential future values and bring them back into today's dollars. How much would we have to invest today to have that amount of money at the end? Similarly, our future value is very similar to the future value formula we computed before. Only now our future value will be present value e to the rm. So we're going to be using m as our variable to represent time, where we can plug in one number for time. When we use t, we're using it as a variable in our calculations. So now we have our two formulas that we need to talk about investing money when we have a continuous income stream. So these are the two formulas that we're going to need. So let's look at some problems and see how we are going to use these in different ways to calculate different things about investments. Example 1, Part A. Suppose you deposit $5,000 when you're 18 years old into an account accumulating 7% interest compounded continuously. What were your total contributions, and how much money will you have at 65 years old? So notice here that we're doing a one-time deposit of $5,000. One of the first things we need to look at when we're doing money problems is whether we're investing multiple times or once. Since this is a one-time deposit, we need to use one of our single payment formulas we talked about at the beginning. So we want to know, what were your total contributions? So since this is a one-time deposit, it's simply the $5,000. We're taking that $5,000 and seeing how it grows over time. We want to know how much money you'll have at 65 years old. So that means we're looking for a future value. So remember, future value was present value e to the RT, because again, we're compounding continuously. Our P is the initial amount that we deposit, so that's our $5,000. Our interest rate here is 7%, so we'll turn that into a decimal, 0.07. And we're leaving this in for 47 years because we're depositing when we're 18, but we're leaving it there until we're 65. So if we do 65 minus 18, we get that this is invested for 47 years. So if we crunch all of those numbers, we're going to get $134,000, $214.32. So that's a pretty good return on our one-time investment. So we made a one-time contribution of $5,000, we left it for 47 years, and now we have $134,214.32. So that's our first example. That was a single payment, and that was our result. Let's look at Part B. Part B. Suppose you deposit $5,000 per year starting when you are 18 years old into an account accumulating 7% interest compounding continuously. What were your total contributions and how much will you have at 65? So notice here in Part B, we're not just doing a one-time deposit. Instead, we're contributing $5,000 every year. So this is going to impact both of our calculations. So let's start with, what were your total contributions? Now, I want you to notice that the interest rate is the same as the last problem, and the amount of time is also the same. The difference is we're contributing $5,000 per year instead of $5,000 one time. And I point this out because everything else remains the same. So you can see the difference between what happens from a one-time contribution to a yearly contribution. So the amount that we invested here, the amount that our total contributions at $5,000 per year, we're doing this for 47 years. So $5,000 a year times 47 years is going to tell us exactly how much of our own money we put in versus how much we earned from interest. So if we multiply those two numbers together, we get $235,000. Okay? So that's how much we put into this whole thing from our hard-earned money. Now, if we want to figure out how much we have at 65, eventually we're going to have to use our same equation that we were looking at before, where future value is going to be present value e to the RM. Remember, we're using M for years when we have continuous payments. The problem is here that we don't have our present value yet. So we can't quite calculate this yet because we need to figure out P. Before, it was straightforward because our P was $5,000. It was a one-time investment. Now, you may think that we can just use the $235,000. However, money is valued differently at different points in time. So our first calculation is going to be to find the present value by using our integral from 0 to M, which here is 47 years. Now, we're going to put in our yearly deposit here, which is $5,000. E to the negative. Now my interest rate is 0.07 T dt. Now, why do we have to use this formula? So having $5,000 deposited 10 years from now, right, is not the same thing as depositing $5,000 today. Money changes its value over time. So we might be able to deposit $3,000 today, which will be worth $5,000 in 10 years. So what this particular calculation does is it figures out the exact amount of money we would have to deposit today to have the same amount of money at the end as if we were to be investing $5,000 a year. So when we do this part of the calculation, you can either do this by hand or you can put this into your calculator. But when you put it all in, you're going to get $68,767.58. So this amount of money is the equivalent lump sum that we could invest today that would give us the same amount as if we were investing $5,000 each and every year. So we're pulling back each of those future payments in today's dollars to get the equivalent lump sum. We need this equivalent lump sum to be able to use our future value formula. So now that we have that, we can go ahead and calculate our future value by doing $68,767.58 times e to the RT. Remember, our interest rate is 7%, and our M here is 47 years. When we crunch all those numbers, we find out that at the end of our investment, we're going to have $1,845,918.83. So remember, our total contributions were $235,000, but at the end of our investment, we have almost $2 million. So this is a pretty solid investment and definitely more than we would have gotten from the one-time payment in Part A. So again, when you have a deposit that's happening yearly, we have to start with the present value formula to figure out what the one-time equivalent lump sum payment was, before we can then use our future value formula to get the total that we'll have in the future. Let's look at another example. Example 2. Find the present and future value of a constant income stream of $200 per month for 10 years, assuming an interest rate of 4% compounded continuously. So, in order to find future value, we have to start with finding present value because we need that calculation to use our future value formula. So we'll start by finding present value first. So present value, again, is going to be the amount of money that we could invest today as a lump sum. That would be the equivalent amount as doing the same amount per year. So when we set up our integral, we're going to go from 0 to m. M is the number of years, which here was 10. Now, S of t is our yearly contribution. I want you to notice here that it's $200 per month. So we have to convert that to be into years. So we need to multiply 200 per month times 12 months per year. So 2,400. E to the negative. Now here my rate is 4%. T dt. So the 200 times 12 is 2,400. So you can just write that in as 2,400. But when we do this calculation, again, the number that we're going to get is the equivalent one-time lump sum that we could make instead of doing payments per month that would give us the same end result. So when we do this, we get $19,780.80. So instead of doing $200 per month every month for 10 years, we could do the same exact outcome by contributing $19,780.80 as a one-time lump sum payment. That's what this calculation is telling us. So now, if we want to find the future value, we're going to do present value, which was the $19,780.80, e to the rm. So we have 0.04. My time m is 10 years. And when I crunch that number, I get $29,509.48. So $200 a month for 10 years. At the end of 10 years, I'll have $29,509.48. That's not bad. So again, in order to calculate a future value, we need a present value. And if we have a constant income stream, then in order to find present value, we have to use our integral equation to figure out this replacement sum that we can use instead of the payments. Let's look at another example. Example 3. Suppose a company wants to have $50,000 in 5 years for a new scholarship they plan to offer. Their investments earn 4% interest, compounded continuously. If regular monthly payments will be used to fund the scholarship, how much should the monthly payment be to achieve this goal? So first we need to figure out what kind of information we have and what kind of information we want. So we want to have $50,000. So that's at the end. So I'm going to write FV. That's a future value. That's how much we want to have at the end of our investment. We also know our M. We know that we have 5 years to make this money. I know my rate R is 4%. And ultimately, what I'm looking for is the amount of a monthly payment. Now, there's no mechanism in our formula to give us a monthly payment. However, we do have a variable that will give us the yearly payment. So remember, S of T is your yearly contribution. And if we have that number, we could certainly divide by 12 to get the monthly payment. So ultimately, what we're trying to figure out is S of T. What is our income stream? So here, because we have future value, we actually have to start with the future value equation and work our way backwards. So when we start with our future value equation, let's remember what that is. We have future value is present value, e to the Rm. Well, what we know is we know our future value needs to be $50,000. We know that our interest rate is 4% and our M is 5 years. So the thing we don't have is our present value, which is not that shocking. So we can solve for present value by dividing both sides by e to the 0.04 times 5. And when we do that, we're going to get that our present value is going to need to be $40,936.54. So if our contributions give us this present value, then we know that we'll hit our future value goal. So how do we take this present value and help us figure out what the monthly payments are? So remember, present value is the integral from 0 to m S of t e to the negative rt dt. Well, we know present value, right? So that's going to go in on the left. So we have $40,936.54 equals, now we have the integral from 0 to m. We know that m is 5 years. We know our e to the negative, now this is 0.04 t dt. And S of t is what we're solving for. Now, I'm hesitating to write it because S of t, as we talked about earlier, is a constant. So like $5,000 a year, $10,000 a year for this particular scenario. That doesn't mean S of t can't be given by a function, but what's implied here is that we're making the same payment every month, and therefore it's constant. If a function is given, then S of t could be a function. But here we know that it's a standard monthly payment, so it's always the same amount. Since it's a constant, that means I can pull it out in front of the integral. That's going to be really helpful for me because now I can solve for S of t. I want you to remember that we can compute the value of the definite integral of e to the negative 0.04 t. Since I can compute that number, that's going to help me solve for s of t. When I compute the value of the integral, I'm going to get 4.53. So that means I can divide both sides by 4.53 to solve for s of t. So 40,936.54 divided by 4.53 is going to give me $9,036.76. So remember, this is my yearly investment I have to make to hit my goal of having $50,000. If I wanted to have the monthly amount, I need to divide that number by 12. So when I divide that $9,000 by 12, I get a monthly payment of $753.06. So in order for this scholarship to happen, this company needs to make a monthly investment of $753.06 every month for 5 years, the end of which they will have the $50,000 that they need to make this scholarship happen. So again, if we're given a future value and we're asked to find a payment, whether it's a yearly payment, a monthly payment, a daily payment, we have to start with our future value and use that to solve for present value. That was step 1. Once we have our present value, we can then use that to solve for our regular payment, s of t. That's step 2. Once you have your answer, it will be in terms of a yearly payment, and you can then modify that to what you need. So if you just need a yearly payment, you're done. If you need a monthly payment, you divide by 12. If you need a daily payment, you would divide by 365. But this is how we plug these things in when we start with our future value. Let's look at one more example where our s of t is not going to be constant. Example 4. Currently, the value of a certain Picasso painting is increasing with time, but the art market has been known to fluctuate. If the price that art buyers are willing to pay for this painting is modeled by p times 3 plus 18 square root of 2t, where time t is in years, and p dollars represents the current value, then what is the optimal time to sell this piece of art, assuming that you have access to continuous compounding at a rate of 5%? So we're trying to value this piece of art. This particular problem is much more complicated than it looks on the surface. So we have this function here that's telling us how the value changes over time. So if we were to put this into the context of present and future value, what this would tell us is the future value of this piece of art in terms of p. Remember, t here is our variable. So remember, future value is going to be present value e to the rm. So what do we know? We know that this function represents our future value. So plugging this in, we have p dollars times 3 plus 18 times the square root of 2t equals present value e to the 0.05. That's our 5% interest rate. Now, normally we'd use an m here, okay? And instead, I'm going to use a t, and I think you'll see why in a minute. So remember, we swapped out our t for an m early on because we were going to be integrating our function. Turns out we're not going to be integrating this particular function, so it's going to make more sense to use t so that it matches the time that we have here. Okay, but both those represent the number of years until we should sell the bottle, or the value after t years. So if we solve for the present value p, which is different than the p dollars, keep that in mind, we're going to get that present value, so we'll put pv to keep it clear. We can divide both sides by e to the 0.05t. And remember, if we divide by an e term to a power, we can bring it up by making that power negative. So our present value is p times 3 plus 18 square root of 2t times e to the negative 0.05t. Now, that represents some sort of number, right? Normally, when we're talking about present value, we'd be taking the future value to solve for something else. But what do we even do with this information? Here we want to optimize the selling time. And if we want to optimize it, that means we want to find the maximum value. So how do we find the maximum of a function? In order to find the maximum of a function, we need to find the critical points. So this problem's taking a turn in a different direction that we've looked at before. Now that we have a way to write the present value, which is the future value, e to the negative rt, we can optimize this by finding the first derivative and seeing where it equals 0. That will optimize our present value and will also tell us the optimal time to sell, because that's when we'll make the most money. So now we have to go back and think about what we know about taking derivatives of functions that have the variable in more than one place. So notice we have a t in the power and we have a t here. P is a constant, so our variable here is going to be t. So when we take the derivative here, we're going to have to use the product rule. Our first function here, which we'll call f, is our p times 3 plus 18 square root of 2t, and our g is going to be e to the negative 0.05t. Notice that we can rewrite f and turn that square root into a 1/2 power. So 3 plus 18 times 2t to the 1/2. Now we can go ahead and find each of their respective derivatives. So for f, we have to use the chain rule. So the p is a constant, so that'll multiply our derivative. Here, the derivative of 3 is 0. And then for our second term, the 1/2 will come down to multiply the 18, giving you 9, 2t to the negative 1/2. But then we have to multiply by the derivative of the inside, which is 2. We can simplify this into p dollars times 18 times 2t to the negative 1/2. So g prime will be negative 0.05 e to the negative 0.05 t. We get the same thing back and we multiply by the derivative of the power. Now the product rule says we're going to do f prime times g plus g prime times f. So what does that look like? So f prime times g will give us p times 18 times 2t to the negative 1/2 times e to the negative 0.05t plus g prime negative 0.05 e to the negative 0.05t times f, which is p times 3 plus 18 times 2t to the 1/2. So our first derivative has a lot of pieces. Notice here that t is our variable, p dollars is a constant, and we want to take our derivative and we want to find out when it equals 0 because we're trying to optimize. So we're looking for critical points. So when we do this and we have an e term, we often want to factor it out. I'm going to factor out both the p and the e because that shows up in both terms and p is a constant. So I have p dollars e to the negative 0.05t. Now from the first term, I'm left with an 18 over the square root of 2t. This term right here is the square root of 2t in the denominator because the power is negative. Then from my second term, I have this minus, which comes from this negative. So 0.05. I've taken out the e. I've taken out the p. So now I'm left with a 3 plus 18 square roots of 2t. And I want to know, when does that equal 0? Now, these first two terms that I factored out are never going to equal 0. that was the benefit of factoring them out. So these will never be 0. Therefore, I have to take what's left and figure out when that equals 0. So I'm going to go ahead and I'm going to graph that on my calculator to find the roots, because it looks like the algebra on this won't be great. So I could take this, set it equal to 0, multiply everything through by the square root of 2t, make a variable substitution to turn it into a quadratic, but it'll be much easier to solve by either graphing it and finding the roots or asking a program like Wolfram Alpha to solve it. When I solve this, I'm going to get that t equals 9.63, which is in years. So this art should be sold in 9.63 years to get the most value for your money. So let's remember where we started and how we got here. We had a function that told us the value of our picture at any time. That was a future value because you'd plug in a different time and that would tell you the value in the future. We used that to get an equation for our present value given the interest rate that we could get on any money that we would invest. From there, we took our present value and we wanted to optimize it. When we want to optimize something, we use first derivatives and set them equal to 0 to find critical points. Here, our critical point happened at 9.63, which tells us that the value will be optimized at that time. This is a very, very complicated problem, and we have all the pieces we need to solve it, but we need to work carefully to understand how to put those pieces together. Look over this a few times and try out similar problems to see if you can get this to work. It's a good method, but we do have to look carefully at it to know exactly what we need to do.